In our first presentation, we'll be talking about something called super heterogeneous receiver, or in short, superheat. It's a type of technique at the receiving end that has been in use since the very beginning of wireless communication. The radio broadcast system uses this technique. Uh, in the case of AM or FM radio, we know that different frequency channels are used by different stations. They transmit at different frequency chunks, so it is frequency division multiplexing. And at the center of the chunk, uh, they have the carrier frequency. Now, the receiver has to be able to tune to any of these frequencies, and it has to amplify the bandwidth. So in this case, the receiver uh, amplifier uh, has two stages. In the beginning, it has a very wide bandwidth support, which covers the whole spectrum. Any channel can be amplified. So this amplifier stage we have right at the. I'm sorry, maybe I quickly go there. So this is the RF amplifier, which sits right next to the antenna. So the first receiver and first amplifier amplifies the whole bandwidth. But for amplifier circuits, you may remember that there is something called gain bandwidth product, which is pretty much constant for a particular design of an amplifier. And it means that if you allow wide bandwidth, you don't have good gain. You see that it has to support the whole frequency range, that uh, so that any broadcast station can be supported. Okay, and the broadcast stations may use any of the frequency chunk within the permissible range. I'll show you the range for AM or FM in different parts of the world. So it has to support the whole range. Uh, for this wide bandwidth support, the gain cannot be good. Um, so with this minimal gain achievement, you have a signal here. So there has to be some provision of high gain amplification. Uh, but to allow high gain amplification, you need small bandwidth. Now note that every transmitting station uses a narrow bandwidth, but the first amplifier needs to support all possible transmitting stations. That is why the bandwidth has to be very wide. But when you receive, uh, I mean, you actually listen to a particular base station, a particular transmitting station. So you at a time don't receive from multiple stations. So at a time, you have a narrow bandwidth reception. So you should be able to use high gain for your amplifier circuit if you can restrict to this narrow bandwidth. But the problem is you don't know where this narrow bandwidth is located. You don't know beforehand. Okay, because you can tune to any frequency. S- So this is why the first amplifier uses low gain. Okay. So the superheterodyne and receiver uses a technique in the next stage so that we can accommodate another amplifier which has a narrow bandwidth as wide as your width for a particular transmitting station. So no matter where that carrier frequency is located, the carrier frequency can be anywhere within the permissible spectrum for AM transmission or AFM transmission. But for this amplifier, the input comes to all, I mean, is the input frequency is translated to a particular uh, chunk, frequency chunk. Okay, I mean, the from the carrier frequency, you actually translate. You move to a particular frequency. Around a particular frequency, you allow the bandwidth of one transmitting station. Okay, so the bandwidth support uh, can be narrow for the second amplifier, which is called intermediate frequency amplifier. We'll talk more about that, and uh, the gain can be very high. Uh, so this particular technique, how you translate, is uh, called super heterodyne. Okay, and the receiver is called super heterodyne receiver, in short, superhet. Now let's look more into it. First, the bandwidth of your audio signal. Okay, your voice is translated into a waveform, and in this waveform, you will find different frequencies if you perform Fourier splitting. The different frequency components you can see, and in the case of human being, the voice uh, waveform ranges from 0 to 20 kilohertz. That's not mentioned here. Okay, so there can be frequency components up to 20 kilohertz. However, most of the high power components lie within 4 kilohertz. So although you can have different frequency components for human speech, you can have components up to 20 kilohertz. Uh, if you use components up to 4 kilohertz, your speech is almost the same. It is almost not distorted. Okay. So up to 4 kilohertz is typically considered for speech conversion. But music instruments generate high power component even at higher frequencies. Up to 5 kilohertz, there are quite a bit of high power components, and up to even for musical instruments up to 15 kilohertz, they produce pretty high power components. I mean, high power components mean that they're significant. You should not cut them off. Okay, so if you want to use high quality music, then you should allow up to 15 kilohertz. And if you uh, are fine with, if you're tolerant with low quality music, and you are more focused on the human speech, then 4 kilohertz is okay, and 5 kilohertz is better. With 5 kilohertz, actually, some music frequency components can be captured. Okay. Uh, so in the case of AM radio, you have more spectrum constraint, and the bandwidth for for audio signal is taken up to 5 kilohertz, or initially in some parts of the world it was 4 kilohertz, later it was increased to 4.5 kilohertz, and in some countries it was 5 kilohertz. Okay. For FM, it has always been 15 kilohertz. So FM radio can reproduce music better. Okay. For speech, you don't have very significant improvement, as I said, above 4 kilohertz. You don't have very high power component. But for music, okay, so the FM radio broadcast that we have definitely produces much better, reproduces the music much better. Okay. Uh, the total bandwidth after modulation is shown here as BT, and that is twice W for AM with double sideband modulation, uh, and the carrier is allowed, the carrier is not suppressed. Mm. For AM radio, we are in this presentation discussing uh, a the radio broadcast basically. Okay, and it has these two types, AM and FM. For this amplitude modulation, uh, the stations use double sideband modulation along with the carrier. They do so to allow cheaper cost for the receiver. You know that single sideband modulation can also reproduce the signal. If you suppress the carrier, you can still reproduce the reproduce the signal at the receiving end. But the receiver circuit will have to be more complicated. The receiver can be the simplest when you have both sidebands along with the carrier. Okay. Now you transmit from just one single station, but on the receiving side, will be thousands of receivers. So if you can allow a simpler circuit at the receiving end, then the overall cost will be much lower. For so many users, thousands or even millions of users can be there. So for all these millions of receivers, you can allow simpler circuit or cheaper circuit. So it makes sense that you use double sideband along with the carrier. Okay. For FM, probably you remember that a number of um, components are created using Bessel function, and uh, the number of components you take, okay, it depends on you how many components you take into account. Uh, so it is shown as here along with the center component uh, and the two side components. It is 2 times d plus 1. Okay. Now let me show you. Before I show the values for BT for them, let me tell you that they are used little differently in different parts of the world, and this division in the world is actually not only for this radio broadcast use, but for many other telecommunication related applications. So they are known as IT region 1 to region 2 and 3. So primarily there are three regions in the world, and we fall in the uh, IT region 3. Okay. And you can see that IT region 1 covers Europe, Africa, Middle East. Okay. In the region 3, we have a good part of Asia and Australia. Now, in many cases, IT region 1 and 3 use the same themes, the same technologies. But IT region 2 almost always differs. Okay, they go differently. And you actually know that that's true for many different cases. It's not only for telecommunication standards, but for many other standards, they take differently. So basically in the world, there are two major sets of standards in practice. Okay. And North and South America, okay, Greenland, they go differently. They take the other side. So a lot of times IT region 1 and 3 merge in terms of the practice. Okay. So we are showing here in colors. As you can see, we are in IT region 3, which covers a good part of Asia. And IT region 1, Middle East, Europe, most part of Soviet Union, Africa, IT region 1. But IT region 2 uh, uses different standards. Okay, now, as I said, that double side bandwidth carrier is used for AM, and the channel bandwidth, I mean BT, is 9 kilohertz for IT regions 1 and 3. And for IT region 2, it is 10 kilohertz. So the value of W is 4.5 in the first two regions, and it is 5 in region 2. In fact, in the past, for regions 1 and 3, it was 4 and here 5. So BT was 8 kilohertz and 10 kilohertz. Later, for regions 1 and 2, it was increased to 4.5. From 4, it was increased to 4.5. The difference was basically, so if you consider the little larger bandwidth, 5 kilohertz, okay, why IT region did that? The only purpose was to include uh, the music components better. Because I said that above 4 kilohertz, human speech has very insignificant components, but musical uh, instruments produce significant components. So when they went up to 5 kilohertz, they had little better capturing of music. So now it is almost the same. 4.5 and 5 doesn't make a significant difference. But when it was 4 and 5, then there was uh, I mean significant. I mean there was a detectable difference between the performance of between the music reproduction. Okay, in this I mean in these two regions. Okay, not in America, the music reproduction was a little better. Okay, now it is almost the same. The spectrum, okay, total spectrum used for AM radio broadcast. Okay, so that is also different in region 2, and with 10 kilohertz spacing. Okay, you know, I mean, you have a good numbering, or I mean, round figures for the different ranges. from 530 to 540, 540 to 550. This way you have bandwidth for different radio stations. And from 530 to up to 1700 kilohertz is allocated for AM broadcast use. So a station can be located anywhere. And please note that uh, it is capturing a good part of the range of in the lower frequency range. Okay, and of course there cannot be any other application, because this radio broadcast takes place nationwide. So the country authority does not allow any other applications within this range. Like in America, there is no other spectrum allocation within from 530 to 700. There in our countries, this range is reserved for the AM use. Okay. Um, these ranges are now with 9 kilohertz spacing. Previously, it was with 8 kilohertz spacing, and you can see that the range is okay. Well, I was little mistaken. I'm showing here the carrier frequencies. Okay, so in the I mean 530 to 5. It's not 530 to 540. It is rather 525 to 535, and then from 535 to 545. Okay, so 530 is the carrier frequency at the center. For IT regions 1 and 3, 531 is the carrier frequency. So the frequency range is 9 kilohertz around this one. So it is like 526.5 through 1606. Sorry, I mean you just have to add 4.5 to 531. Okay, so 535.5 for the first channel. So this way you have 9 kilohertz channels on and on. For AM, it is the same in all ITU regions. It's always 200 kilohertz. Okay, taking uh, I think the value of D is 6 or 7. I forgot. Okay, you can calculate and find out how many it is. Okay, so how many Bessel components you take. Okay, so with sufficient number of Bessel components, a range of 200 kilohertz is taken, and then the spectrum allocation is the same in all IT regions, 88 through 108 megahertz. So your FM radio, I mean, when you use scanning with FM radio, it to check where the transmissions are available. So it scans from 88 through 108 megahertz. Okay, at 0.2 megahertz spacing. Now we will discuss how you translate the frequency. Okay, you may be capturing any radio station, so the carrier frequency can be anywhere within the permissible spectrum. Now what is done when you actually perform tuning, you there is a tuning circuit to allow filtering around a particular carrier. Okay, so the amplifier can support all the carrier frequencies, but you don't collect the whole spectrum. Rather, there is a tuning circuit, if some filtering next to the antenna, and before you amplify through your first amplifier stage, RF amplifier stage, which allows 200 kilohertz, no, sorry, I mean 9 kilohertz or 10 kilohertz, okay, for say AM radio broadcast. Uh, and it it will just tune to different carrier frequencies as you rotate the knob. So this way you tune to different frequencies, and different 9 kilohertz chunk actually passes through the first amplifier. But wherever it is, this 9 kilohertz chunk is located, it can be amplified because this amplifier supports wide bandwidth. Now, when you tune there, at the same time, a signal, I mean, an oscillator frequency is adjusted. This oscillator generates a signal, and this signal is mixed with the signal at the output of your RF amplifier. So XT is mixed with the signal generated here. Now this carrier frequency of this oscillator F1, okay, I'll show you here. Okay, has a carrier, has a center frequency FLO. It's called local oscillator. So the frequency we are calling FLO. So when you mix, it is similar with modulator operation. Like when you perform modulation, I mean you generate two side components, like, which is the you add and subtract. Okay, so it generates, after mixing, it generates components FC plus FIF. Okay, well, sorry, this carrier frequency, so this local oscillator frequency, which is adjusted as you tune. Okay. Oh, by the way, let me check with you. You can hear me, right? How's is there any problem with the bandwidth today?
No, sir, it's okay.
No,
It's
sir.
okay. Okay, thank you. Okay, so when you tune, the oscillator frequency is also adjusted. Okay, simultaneously it is adjusted. And how is it adjusted? The carrier frequency, as you're tuning, you are actually changing your carrier frequency. You want to switch to different station, so the carrier frequency is adjusted. So here FLO will be the carrier frequency, that carrier frequency added with a fixed frequency FIF, just called intermediate frequency. Okay. I think in the previous slide, so this is called IF, or intermediate frequency, and that is a fixed value. For AM it is 455 kilohertz, for FM it is 10.7 megahertz, so it is fixed. Now as we have this FLO, when you mix it with your output from RF amplifier, what happens? The new generated frequencies will be FLO plus FC and FLO minus FC. Okay, similar with the module signals generated out of modulation. Okay, the mixing operation generates these two components. Now note that FLO is actually FC plus FIF. So you get a component 2FC plus FIF, and also you get a component only FIF. FLO is FC plus FIF. When you subtract FC, you are left with FIF. So you have two components after mixing operation, FIF and FIF plus 2FC. The upper component here, FIF plus 2FC, is quite a bit apart, because you're adding 2FC. So using a filter, this upper component is removed. So you are left with only FIF component. Okay. So actually, you have the whole 9 kilohertz or 10 kilohertz spectrum around this FIF. Okay. After mixing and filtering, you are left with the whole, or I mean, audio bandwidth, or I mean, transmitted bandwidth, BT, around this FIF now. So it was when you captured, you had the bandwidth around FC, but after this mixing and filtering operation, you have the same bandwidth translated to a frequency around FIF. And FIF has a fixed value. It is 455 megahertz, or so you have some fixed values for AM and FM operations, meaning that the next amplifier, okay, 455 kilohertz, 10.7 megahertz. So this IF amplifier will be able to work around this frequency, I mean 9 or 10 kilohertz bandwidth, around 455 kilohertz or 10.7 megahertz. Okay. So it has a fixed location. In the case of RF amplifier, it could be located anywhere, but now you have a fixed location in frequency around this FIF. You have a range. Okay, so here it was around FC. Now we have around FIF. So the bandwidth support can be very small, only 9 or 10 kilohertz, and you can use, or I mean, in FM it will be 200 kilohertz. Okay, so you can have very good gain here. Okay, the real gain, the real amplification takes place at this stage. So after this amplification, it goes through a demodulator circuit. I'm sure you covered the demodulator circuits for AM and FM cases. Okay, so thereafter you let it pass through a low pass filter, and only the W bandwidth is then fed to the speaker. Okay. So I have already explained it. Now, I mean, in this slides, it is also written. The IF amplifier, okay, operating around intermittent frequency can have very good gain because of very small bandwidth. Okay, so you have these components. Okay, remember that these frequencies are fixed for all radio broadcasting. Okay, I think all these things are explained. So a small thing we need to talk about image signal. So a problem can arise for when you have an image, I mean, you have a radio, sorry, you are capturing a station with carrier frequency FC. But there is also another station transmitting at a frequency which is Fi. Okay, where Fi and Fc are related this way. So if it is the case that you, both signals enter the receiver circuit, okay, then what happens if this Fi also is translated to the same FIF, okay, because if both signals can enter the receiver circuit, okay, so you see with an example that an incoming carrier frequency is 1000 kilohertz and the local oscillator is will have a generation of 1455 FC plus FIF, that will be FLO. Okay. Now, if you have another signal at 1910, okay, which is away from your intended carrier frequency by twice of 455, right? 1000 plus 2 times 455 gives you 1910. Okay. Then when this signal will go through the mixing operation, what will happen? You have a generation of carrier oscillator 1455, and at the input you have 1910. So the mixing operation generates 455, right? So like, you this incoming frequency 100, okay, after mixing operation generates 455, which is the intermediate frequency carrier, and that is fed to the IF amplifier, right? Because you subtract 1000 from 1455, so you get a component around 455. But this one will also generate a signal around 455, because here you subtract this 1910, you subtract this oscillator signal frequency 455 from 1910, and you are left with again 455. So both the signals from this second station will also be fed to the IF amplifier. So there will actually be an interference. Okay, this station will interfere. Okay, it will be overlapped onto your intended signal. So that's a problem, and both carriers will be. So what you need to do, you need to allow a filter so that the image signals cannot enter. Okay. So the e- e- to stop the image signal, the bandwidth, okay, has to the filter has to eliminate these upper frequencies. So the difference between the carrier and the image is 2IF. Okay, so if you allow a filtering, that allows on, I mean, BT, okay, and the upper frequency, uh, frequency by 2IF, okay, is I mean, cannot pass through, okay, then you are safe. Only this signal will be uh, will go through the circuit. Okay. So with that, we complete this discussion on super heterodyne receiver. And questions?
No, sir.
Okay, then we will move to our next discussion, and that will be an example of LOS communication. We are using examples for better clarification of the challenges that we have setting up wireless communication. And uh, after um, this um, upcoming presentation, we'll have another presentation discussing link budget, where we will uh, determine what power levels we need to set at the transmitting end, considering the all the different uh, power losses on the way and the requirement at the receiving end. So that is called link budget calculation. Uh, so then uh, you should try to incorporate all different type of uh, power losses on the way, and we will do that for two different example cases: LOS case and non-LOS case. uh, so uh, for non-LOS case, we have been using the example of cellular communication because that incorporates the uh, maximum challenges. For LOS case, we will be using the example of satellite communication, because in the case of satellite communication, you have the farthest communication link. The distance between your transmitter and the receiver is the maximum for satellite. And uh, in this case, you have the maximum path loss. You need high antenna gain. Mhm. So out of all different examples, you have the maximum challenge for LOS communication. Okay. And before we get to that link budget calculation, I think it will be good that we know a little bit more about this satellite communication. Okay, it will then be easier for us to discuss issues with satellite communication. So our next discussion will be on satellite communication. Satellite services as an example of LOS communication we will discuss now. The satellites can be located at different heights from the Earth, and this this is how they are categorized into GO, MEO, and LEO. Okay. For GO, the height is fixed, the altitude is fixed. But for the other categories, MEO or LEO, you have a range. Okay. From 2000 to 36,000 kilometers is the range for MEO. The satellites can be at different heights. for LEO, they can be at different heights. Some LEO satellites are very close. You can see that even less than 1,000 kilometers. And I'm not sure if you know, some satellites are actually visible from Earth. At night, if you look at the sky,
Yes, sir.
sometimes it will be possible for you to uh, see something that is little bit shining. Okay, and it will be moving, and I mean, after a while you lose it. Okay, so uh, with your response, I feel better. Probably you have already noticed it. Very good. Um so,
Yes.
some LEO satellites are visible, and that's very interesting. Um, okay, now in the case of GEO satellites, they have fixed position compared to any position in the Earth. Okay, I mean, we are rotating. The Earth is rotating. We are rotating, and the satellite is rotating at the same velocity. So the relative position compared to uh, any position on the Earth is fixed, and that is the beauty of GEO satellites. That's why it is most popular. In uh, the orbital period, okay, that how long it takes to complete completes the revolution around the Earth is the same as the rotation period of the Earth. Okay, so how is it done? It's actually nothing complicated. You all can find out uh, how you can set a velocity for the satellite at a particular height so that it becomes same. Uh, I mean, with absolute circular uh, I mean consideration, it will be easy calculation for you. Although it is not exactly circular in
It's kind of
reality.
like with that escape velocity, right, sir? With that
Yeah, yeah.
escape velocity and all.
No, it's not. It's not about escape velocity.
Yes.
What I'm talking about, escape velocity is what you need to uh, get off, okay, from the Earth.
Okay.
You need a velocity
Okay, sir.
when you
Yes.
launch. In the case
Yes.
of satellites,
Yes.
they are launched. They are loaded on a rocket. Okay, and the
Yes, sir.
rockets settle on the orbit, and thereafter the rocket launches the satellite. It gives a velocity to the satellite. Okay, so they are loaded
Yes,
on
sir.
a rocket, and the rocket is launched. Then you need the escape velocity when you launch the rocket, and thereafter when the rocket launches the satellite, I mean, it gives a velocity. I'm talking about that velocity. Then it is
Okay, sir.
taken to a particular height. Okay, so this, it's a well calculated height, and the velocity given to the satellite is also well calculated. So when it is GEO, then I mean, the way it works, that you need to have the centripetal force and the centrifugal force equal. I mean, the uh, because it is because of the rotation, it will get a force, outward force, and you have a gravitational
Yes.
force. You The satellite is located there, so the Earth will attract the satellite. So there's a gravitational force, and because of the rotation, because of just the uh, I mean rotational speed, it will get an outward force. So these forces become equal, and that is how the satellite will be stable on the orbit. Okay. Now, this
Yes.
velocity, all of you can calculate easily. If you consider pure circular case, then all of you can easily calculate uh, from the masses. You calculate the force, and if you know the distance, if you know the height from the earth, how much away it is, if you know this distance, then you can calculate, I mean, the attractive force, and also how much velocity you need there to have the same force, to have the forces equal. So that's a very simple calculation, right? Now, with this particular velocity, uh,
Yes.
you definitely can also calculate the angular velocity, and then you can calculate how quickly uh, it completes the revolution, or I mean, how long it takes to complete one whole revolution. Okay, then you need to set this whole complete revolution period to be the rotation period of Earth, which is, approximately 24 hours. Okay, for this uh, particular, so you understand that the angular velocity uh, has to be has to have a particular value, so that the rotation period for the Earth satellite completes the whole revolution around the Earth in 24 hours approximately. Okay. Uh, uh, by approximately, I mean that it is, the rotation period is not exactly 24 hours. The exact value is little different. So in the case of satellite rotation period, it has to be equal to that exact figure. Okay. Now, this when you set it to that 24 hours, then you will find that it is possible, okay, to have a, I mean, to have it uh, for this particular rotation period, uh, you will end up with a particular distance from the Earth. Only one uh, distance solution can allow you this particular rotation period. Okay, and that distance is 35,786 kilometer, or 22,236 miles. Okay, so this is how you have a fixed altitude for all geo satellites. The their I mean, purpose is to have a fixed location on the sky. When you have an equal rotation period, then you have a fixed location. And how is it advantageous? When you have a fixed location, from the receiving end, you can direct your antenna towards that fixed point. You don't have to track, you don't have to change the direction of your antenna, because the satellite has a fixed position on the sky.
Yes.
Okay, so that is the advantage. In the case of satellite, as I said, the distance is the maximum. And we know for longer distance, you have a larger path loss. So you have actually incredible path loss. So in this case, what do you need? You need more directional antenna. As with a longer distance, you have to, if you allow spreading, then more and more energy will be wasted. The larger the distance between the transmitter and the receiver, the more it is required that you have narrower beam. You better pinpoint towards your receiver, because the energy will be spreading and spreading on the way. You get a smaller and smaller share as you have further distance. Okay, so it is more important that you have large gain for your antennas when your distance is large. Try to make the antenna radiation beam as narrow as possible. Okay, just pinpoint your receiver. And for this purpose, the there are very large Earth stations you will be visiting if we don't, after this COVID situation, inshallah, it will be possible to have the industrial tours. And our industrial tools cover uh, a visit to Banani Earth Station, and I think sometimes they also visit the Gazipur station. Okay. So you'll find that the Earth station, the dish antenna, uh, has a dish like I would say larger than a two-storied building. Okay, uh,
Yes, sir.
larger than two-storied building. I mean, almost a three-storied building. It is as large as a three-storied building. Okay.
Okay,
So
sir.
with this, because with this larger dish, you can have more directional beam for both transmission and reception, and that helps. And with this kind of directional ray antennas, it is difficult to track. If your satellite keeps moving, your antenna also has to track accordingly, and that is not easy. Okay. So it is, I mean, it will be, and you have to meticulously point when you're using narrow beam, then you also have to be very cautious with the direction. You have to, because if it is little misaligned, then you'll be losing the whole signal. Okay, so the alignment is also very important. So if it tracks, then the alignment is also more challenging. Okay, so when you don't have to track, then the alignment, you just set it once, and so it is easier. Okay. So this is why geo satellites in the past were mostly launched, mostly used, and key applications of satellites were all geo. However, for geo satellites on one side, there are limitations. How many satellites you can put on the sky? You have to put them around the um, equator. I mean, on above the Earth's equator. You you have to put them so you cover both sides of the equators. Okay. It cannot cover. Well, let me tell you that with 3 geo satellites, you can cover the whole periphery around the Earth. You set one above the equator at one point. Then, if you take uh, 2 others, okay, equally spaced around the equator, then it is possible to cover the whole periphery on the Earth. However, towards the pole, there will be some parts left which are not covered. So geosatellites cannot cover the polar regions, but that's fine. That's a very, I mean, that's actually the unused part of the world. Okay.
Yes, sir.
So uh, geosatellites are a very good choice, and for the uh, TV broadcast, satellite-based TV broadcast, geo satellites are used, so the users don't have to change the direction they track. Okay, we'll talk more about that. We have a satellite now. We'll talk about that. However, for the other 2 options, you have to track, or you have to have a provision for capturing for multiple satellites. Okay. So MEO or LEO satellites will be moving on the sky. So we'll use example applications for GEO and LEO to explain how we can. Okay, the basic circuit blocks for are the stations. Okay, so when you are transmitting, um, you use again some actually intermediate frequency modulator and some amplification there, and thereafter you translate to whatever carrier frequency you need to use. Okay, so there will be different channels. A particular satellite supports a number of channels, many different, like it's like FDM. Different channels will be using different frequency chunks, so you translate to different carrier frequencies, and thereafter you amplify. Of course you need very high power amplification because you need high power transmission. With high, even with high gain antenna, to cover the large path loss, you definitely need very high power at the transmitting end. Okay. Uh, Now on the satellite, it is called transponder. Okay. Uh, we assume here an operation like what is done in the case of TV broadcast. Okay. However, in this example, we are showing uh, what can be done for analog case. Actually, for digital broadcast, it is also possible, okay, to use this same circuit block, but it is also possible that you convert, you get the digital signals back, and then you again reproduce them. It's also possible. But anyway, uh, if I mean, this block is applicable for any type of signals, analog or digital. I mean, it will work. Basically, it will work. So you see that first you receive the signal and let it pass through a band pass filter, and then there is an amplifier, low noise amplifier on the receiving side. Uh, Typically, the first amplifier is designed with very low noise addition. Okay. We probably discussed during noise presentation that the noise levels get amplified on the way. Okay. When you have different amplifier stages, every amplifier stage will add some noise. I mean, all circuit blocks add some noise from themselves. The next amplifier will amplify the noise also. I mean, every every amplifier will amplify the signal fed to itself. So the noise generated by the previous amplifier stage will also be amplified. This means that if you have a number of amplifier stages, which is required for LOS communication when you struggle with large path loss, so you have multiple amplifier stages. So then the earlier the amplifier stage, the more your system is sensitive to noise. I mean, this amplifier, if generates noise, this noise will be generated by all the subsequent amplifiers. A later amplifier stage will not be that sensitive to noise. If the so the noise generated by the last amplifier will not be will not be amplified by another amplifier. Okay. So the earlier the amplifier stage is, the more you have to be careful with its noise generation. So especially the first amplifier. So with for the first amplifier, there is a specific way of design to minimize the noise, and it is called low noise amplifier, LNA. There is a course in fourth year microwave engineering where we discuss the design for low noise amplifier, okay, the special technique for low noise amplifier. All these are operations at very high frequencies. That microwave engineering course is dedicated for high frequency circuits. Okay. So there are different approaches for high frequency circuit calculation. The ordinary approaches don't work there. So these different approaches covered in that course. Anyway, after this LNA operation, the signal is like the let me check what time it is.
So it's almost once.
It is almost one. Okay. Do you have any questions? I think it is better that.
So we can stop here. From next class, we can start with the
Okay.
circuit, sir.
Okay.
Inshallah.
Now we need to schedule. Sorry, I was supposed to talk to the CR.
Yes,
Okay,
sir.
I'll do it.
About the quiz.
I'll do it today.
Okay,
I'll do
sir.
it today, and inshallah, declare the schedule and syllabus for our
And
third
sir, also
class.
about that assignment, sir, if you could consider, so that would also be helpful, sir.
Okay.
It's like you could give
Well,
the assignment now, sir, and since we have like 5 days off, sir, so like on a later date, sir, not in the 5 days, we could also submit it, sir. So
do you
so
have any vacation? I mean, what
money,
do you
yes,
mean?
sir. We
What
have
do you
a
mean?
break, sir, in this coming week, sir. Yes, sir. We have been granted 5
স্যার
days.
সামনের
Oh,
উইকটা স্যার
really?
আমাদের 1 উইক হচ্ছে একাডেমিক্স অফ স্যার
Yes,
Oh, really?
yes,
ইয়েস
sir.
স্যার
স্যার আজকেও বন্ধ ছিল বেসিক্যালি।
হ্যাঁ,
Or,
অসুবিধা নেই, ওগুলো
I
ঠিক
mean,
আছে, স্যার।
so I mean, this coming week is off. I mean, this
Yes, up to next Sunday, sir. Yes, sir.
up to next Sunday, I mean 15th of August.
Yes, sir.
Yes, sir.
16 থেকে সব শুরু হবে।
Oh, really?
Yes,
Okay. So I heard that you had applied for
yes,
a
sir.
break due to COVID
Yes.
situation.
Yes,
So,
sir.
so is that? I mean, is it granted? I mean, it's
Yes, sir.
for
It has
for
been
that
Yes,
granted,
sir.
sir,
It
on
has been
Thursday,
granted
sir.
for a
Yes,
week.
sir.
Okay,
Yes, sir.
okay, okay. You know, we are not going to our university, so sometimes we are in the dark. We're not
Yes, sir.
updated.
Yes, sir. No problem.
Okay, okay. Then I'll meet you again on
16th, sir.
yeah,
No,
so
sorry,
on
17th, sir.
17th,
17th. Yes, sir. 17th.
17th of this month.
Yes, sir.
Okay, meanwhile, I'll talk about both your class test and
The assignment, sir, if you
assignment.
want to
Okay,
give,
স্যার
sir. Yes, sir.
অ্যাসাইনমেন্টটা একটু কনসিডার করেন স্যার, কারণ স্যার ফাইনালও
okay,
আবার কাছাকাছি চলে আসতেছে স্যার।
okay. So is the date for your final exam is, I mean, is it also shifted?
So we are not sure about that, sir.
Yes,
Okay,
sir. It's
Okay,
all
sir. It
shifted,
is.
sir.
Okay, it's
Because
all shifted.
okay,
in this week there is a hiatus of from all the academic activities, sir. So
okay,
all is
okay,
halted for
okay,
1 week.
okay, okay, okay. So I'll see you later.
Yes, sir. Inshallah, sir.
Jazakallah
Sir,
for
you
your
also
time.
take rest, sir. Also, you were sick, sir. So it's just a good time for you to rest, sir. Yes, sir.
Yes. Okay,
Actually, sir,
thank
many
you.
of us is
Thank you very much.
Assalamu alaikum, sir.
Walaikum salam.
Keep us in your prayers.
Jazakallah. You also do that, inshallah.
Sure.